Okay, so now we're going to do an example of variation of parameters. So this is from the textbook. TB stands for textbook from section 4.6, number 6. We want to solve the differential equation y double prime plus y equals secant squared of x. Okay, so this is again second order differential equation, and your g of x here, or f of x, either way, is secant squared of x. And because it's not sine or cosine, it's not e to the x, we have to use variation of parameters, right? The method of undetermined coefficients will not work for this problem. Okay, so first thing we need is our fundamental set of solutions, right? We need our complementary solutions. So say yc here, right? So, well, let's see. So the auxiliary equation, characteristic equation, is just m squared plus 1 equals 0. And we know that that has two solutions, plus or minus I. So instead of using e to the ix, we'll use Euler's formula and write the complementary solution, as always, as c1 cosine x plus c2 sine x. Okay, right. Okay. So now we need the particular, actually, before we do the particular solutions, remember y1 we'll say is cosine and y2 is sine. That's going to be important. Okay. So now what do we need? Well, now we need the formula for the particular solution, right? So, in fact, let me just give you the whole general solution. Again, you can look it up, or on a test it'll be here. So it's going to be c1 y1 plus c2 y2, and then minus y1 times the definite integral from x0 to x of y2 of t times f of t divided by the Wronskian w, right? Integrate with respect to t here. Plus y2, definite integral from x0 to x of y1 of t, f of t, all over w of t. So the Wronskian in general will be a function of time, or t. Yeah, so t usually stands for time, but not in this case. T is just a dummy variable here. Okay, so that's the formula, right? So now let's see, how do we actually use that here? Well, first thing I think we should calculate is the Wronskian, right? And the Wronskian is going to be the determinant. Let me make that a little more vertical. This is going to be the determinant y1, y2, and then the second row will be y1 prime, y2 prime. So I think in this case, here's y1 cosine x, and y2 is sine x, and y1 prime, the derivative of cosine x, is just negative sine x, and y2 prime is cosine x. So to take the determinant, you multiply the diagonals. Cosine times cosine is cosine squared, and then minus this diagonal will be negative sine squared. So of course that just gives you cosine squared plus sine squared, which I'm sure you all know is 1. That's the Pythagorean identity. So this is very convenient because, right, the denominators here are just going to be 1s, right? Okay, so now let's evaluate these integrals here, right? So let's start with the first one. This is the definite integral from x0 or 0, either way, to x. Y2, of course, is sine, but this is y2 of t, right? So this is going to be sine of t. And then f of t is secant squared of t. Sorry, secant squared of t. Divided by 1, because the Wronskian is 1, dt, right? So x0 to x. So we have the definite integral of sine divided by cosine squared. So that's just going to be, let's see, sine over cosine is tangent, 1 over cosine is secant. So this is really just secant t times tangent t dt. So hopefully you remember what that is. That's a Calc 1 problem. The derivative of secant is secant tangent, so the integral of secant tangent is secant, right? So this is just going to be secant x, obviously minus secant of x0, but as I think I said in the last video, we're going to ignore that because it's just a constant, right? So that's the first integral here. The other integral is going to be y1 is cosine of t. I'm not going to use parentheses here, right? So cosine t times f of t is still secant squared of t dt divided by 1. And so that's going to be cosine divided by cosine squared, which is, well, 1 over cosine, also known as secant. So now we have to integrate secant. Yep, remember that one? Yeah, now I'm trying to remember it myself. I think it's natural log absolute value of secant plus tangent. Right, plus c. Well, yeah, it's not. I mean, we're treating this as an indefinite integral, right? We're going to ignore the x0 part for the same reason. All right, so now I think we can put this all together. So let me go back to, well, yeah, so let's do it this way. So y of x is going to be c1 times y1, which is cosine of x, plus c2 times y2, which is sine of x, and then minus y1, which is cosine of x. Right? So yeah, this is y1 of x, right? Of x, y2 of x, right? Times this integral, which was secant of x. Try that again. Secant of x, right? And then plus y2, which is sine of x, times this integral here, which we found was natural log of secant plus tangents. So times natural log of absolute value of secant plus tangents. And I know I've said a million times we can ignore the absolute value. We're going to keep it here, I think, because you never know when this might end up being a negative. So I guess that's the solution. Oh, we can do one thing here, right? This is just cosine divided by cosine. This is just equal to 1. So why don't we simplify that? So we still have c1 cosine x plus c2 sine x minus 1 plus, and then I'm debating about whether I should use parentheses here. Sure, so sine x times the natural log of secant x plus tangent x. And I don't think there's any way we can simplify any of that. So that is our solution to the original equation, right? Yep, so that's how variation of parameters works. That's what I would expect you to do, say, either on a test or in the homework. You don't have to actually go through the whole method of variation of parameters. You just have to be able to find the Wronskian and evaluate these integrals if they are integrable, and they were here. And I would assume in most of the problems in the homework they will be. If there are problems where you get some weird integral like the integral of e to the x squared, then you just leave it as an integral, because it's impossible to evaluate in terms of elementary functions. So I think that's it for this example.